Start recording. I'm going to continue. So then let's continue with this. Got my pen? Yeah. So this says a point charge X is located some distance from a point charge Y. So let's do that X and let's do that Y. And charge X experiences a force of 18 newtons towards Y. So let's visualize that. And then it says, what can you conclude about the sign of the two charges? What do you think? They've got to be different, don't they? Because that's an attractive force. So they have to be different. You know that just from the conceptual side. And then what size of force is experienced by charged Y? It's going to be 18 newtons because why is this 18 newtons? Whose law? Newton's third law? Action-reaction pair? And then what direction will the force on charge Y point? It's going to be towards charge X. So that's going to be towards charge X. And then what can you conclude about the magnitude of the two charges? X equals Y. X is twice than Y. X is half than Y, or nothing. I want you to think. I want you to commit. And I'm going to have a show of hands. Okay? So think about it. Think about it. All right. Who thinks A? Who thinks B? Who thinks C? Who thinks D? Who's not put their hand up? Commit. Just decide. Just what do you think is best? Commit.
Is the magnitude always positive or not?
Who thinks A? Who thinks B? Who thinks C? Who thinks D? The answer is D. You see, if you think about it, that force is equal to KE little q big Q over R squared. And the two forces are going to be equal even though the two charges are not equal. Yeah? The moon pulls the earth with the same force as the earth pulls the moon. So it's so tempting to say they're the same. It's like that's the common kind of conceptual trap. You say, oh, the same forces, same charges. It just turns out it's not true. You can't get that. So this is just call it chestnut. This is a common misconception. You can't tell anything. They could be the same. They could be different. There's nothing to say they're a certain ratio. It's just they both happen to always be the same size because it's an action-reaction pair. So can you see this is where reading around the subject and experience and going back and getting hold of an old copy of that conceptual physics book, and even though you passed that course, just reading through it basically takes this and just improves your conceptual understanding. So it becomes more solid. You make fewer kind of like, oh man, yeah, that's not true. You make fewer mistakes. You don't have time to get fully solid on all the conceptual stuff. When I did teacher training, I had a master's degree. Well, I was on my master's degree in physics, and conceptually I was falling apart. And my teacher trainer said, of course you're falling apart. It's the last thing people always get. You know, in my day, they assumed if you knew the math, you knew the concepts. And in fact, no one does it that way. The numbers are our security. And then when we start thinking about it, we go, oh man, that's true. So concepts for most of us come last. So don't think because you did concepts first that it's the easy stuff. It's not. It's often the hardest stuff. So don't be upset with yourself when you make a mistake like that. Pretty well everybody does. But just recognize, so go back and comb that hair a little bit more and get rid of some of those misunderstandings. There's always stuff. Sometimes I get a student who's got an AP in physics and they go, do I need to do general physics because I have an AP in physics? And I tell them with my hand on my heart, I've been doing this for about 25 years, and every semester there's this one time when something happens and I go, oh, that's why it's like that. And it gets that little bit easier. So redoing it once is actually, you get a lot out of it. Point charge X is located some distance from point charge Y, so we have X and Y. 18 newtons to O, so there's 18 newtons. I hope this is not the same slide. What force would charge Y experience if the separation between the two charges were tripled? So now we have X and we have 1, 2, 3, and now we have Y. So what would that be now? So what do you think? Let's have a look. 3 times further away means 1/9 the force, which means you go from 18 down to 2. How can we do that so it's not in our heads? This is how you do it. You go, well, my force is equal to KE QQ over R squared. I might have run out of space here. So my force new over my force old is equal to my KE new, Q new, Q new over R new squared divided by KE Q old, big Q old over R old squared, which equals, well, the KE's don't change, so just leave them as 1 and 1, or KE and KE. And what did I change? Oh, Q new did not change, so that's 1, and Q old was 1, and little big Q was the same as the old Q, so leave those as 1 and 1. The only thing you did change was this R became 3 times bigger than the old one, and you've got to square it. So that equals, 1 over 9, doesn't it? So then you say, well, F new over 18 is equal to 1 over 9. So F new is equal to 18 over 9, which equals 2 newtons. You know, doing it in your head is fine, but you'll make slips. And if you want to cut down on the number of slips, just get the layout. Okay. Let's do one where you might need the layout a bit more. What force would point X experience if the separation between the two charges were tripled, the magnitude of charge X was doubled, and the magnitude of charge Y was quadrupled? So I'm going to say, well, F new over F old is equal to KE new, Q new, big Q new, separation new squared, over, always put the new over the old, KE old, Q old, big Q old, over R old squared. And now you start thinking about your numbers. And you say, well, if the separation between the two charges were tripled, so then let's put down 3 squared on the top and 1 squared on the bottom. So that's that taken care of. And then the magnitude of charge X is doubled. So let's go this 2 and 1. And then the magnitude of Y was quadruple. That's 4 and 1. And then you can either leave the KE's as KE's, or you can just call them 1 and 1, because they're not changing. It doesn't matter. That's going to be 2 times 4 is 8 over 9. So now Fn over the old value, and the old value was 18, Fn over 18 is equal to 8 over 9. So Fn is equal to 8 times 18 over 9. Fn is equal to 2 8s, so 16 newtons. 16 newtons. And I just feel that doing that in your head in a test when you're a bit rushed might cause you might make more slips. So. Questions? Okay. Let's get a bit more general in our layout. Let's say we have a whole bunch of charges and we want to know the effect on the charge in the middle. So here's my charge in the middle, and I want to know the effect caused by Q3, Q2, Q1, Q4. First of all, what's in comparison with Q, little q, what's the sign of Q1? Same or opposite? How do you know? Attractive, yeah. So this opposite signs. What about Q2? They're the same, aren't they? Because it's pushing away. What about Q3? Going to be opposite. What about Q4? Opposite. So the name of the game with this is we figure out the vectors. There's going to be 1, 2, 3, 4 of them, and we add them up. That's what that means. That says each vector, we'll call this an ith vector. I is 1, I is 2, I is 3, I is 4. And we have the sum of them, and the sum of them, well, each one is Ke times the one charge times the other charge times the separation between them squared, multiplied by the unit vector in that direction. So it's the same form we've had before, it's just now we're going to add a whole bunch of them together. And so here's a typical book example. And what I feel about these examples, some reason why I don't like these examples particularly is because I remember when I first did them, I found them really hard until I had seen them. So the first time through was like pulling teeth. I didn't get them. And then once I'd seen them, it was like, oh yeah, this is, because there's little tricks involved. And I tend not to like things where there's little tricks. Now, I could argue and say, well, if you did your homework, you'd have seen it before. But I like it to be not so, I don't like it to be like I'm teaching you a secret handshake that, you know, is just like between us. And if you're there on the day, you have this tremendous advantage. So I don't like these so much, but it's a good principle. It kind of shows some things. So it's not to say you won't get one, but it's relatively low on my list. So what goes on here? We say we have 4 equal positive charges that lay at points indicated in the diagram. So there's 4 charges. The yellow ones are charges. And the magnitude of the force experienced by charge X, so there's charge X, because of charge Y, there's charge Y, is going to be 3 newtons. Let's have a look. Positive charges, so it's going to be like that. That's going to be 3 newtons. They're all positive, so 3 newtons. They're all 2 meters away. They're all the same charge. Okay, so now that's just given me a scaling. That's just a bit of scaling. Because now what it says is, okay, what is the magnitude and direction of the force experienced by charge Z? So it's charge W on Z, charge X on Z, and charge Y on Z. From what I just told you, which way will Y cause the force on Z to point? Will it be towards Y or away from Y? Away from Y. Which way will charge X cause the charge on Z to point? Away. Which way will charge W cause the charge on Z to point? Away. And what's the magnitude of each one of these arrows? 3 newtons, it tells you. It's 3 newtons, 3 newtons, 3 newtons. And then, okay, I want to find the magnitude and direction. So there's a little bit of a conceptual thing here. Hopefully from Physics 1 you got the idea about, oh, look vertically and look horizontally. So let's divide this up into 2 components. So I didn't mean to do that, meant to do that, meant to do that. And let's do green. So let's divide this up into 2 components. Now, what can you tell me about the sum of the vertical components? Yes. The force in the y direction equals 0 newtons, because they cancel each other out. So there's only components in the x direction. The force in the x direction is going to equal to, what's this going to be, 3 newtons? Plus, what is this component going to be? 3 cosine 60. You know it's 60 because it's an equilateral triangle. And then we have this guy down here, which is 3 cosine 60. And what is 3 cosine 60? 3 plus 1.5 plus 1.5. Fx is equal to 6 newtons. And I don't know why, I just feel it's kind of like it's about everything but adding them together. I just feel like I've always kind of felt, oh man. Anyway, so there's a typical back of the book question. Okay.
And it'll be to the right.
Oh, it's to the right, yes. Yes. I'm sorry, yeah, it's 6 to the right, yeah. Because that's where they're pointing, yeah. It's that summation, yeah. Yeah. Yes?
So wait, why is it 60 again? How do you know it's
180 degrees in a triangle, and 2 and 2 and 2 means they're equal lengths.
Okay.
So what is that, an isosceles or an equilateral? Is that right?
Yeah.
No.
Isosceles is 2 sides of the same line.
You see, I need to go home and get my old math book out and relearn some of that, because you use it once every 5 years or something. Don't tell Dr. Sorich that. Last little bit, we've only got a few minutes, but I want to set you up for next time. So the problem with all this is that you've got to put a force, you've got to put a point at the point of interest. You've got to put a charge at the point of interest. But supposing I'm interested in that point there, or that point here, or this point there, or that point there, what I find is, if I could somehow move a test charge around, I could build up a map. It's a bit like, I can have a map and it shows the contour lines for a valley that I'm on. And I can even be a bit cute and have those joined together, so I know that the top of the valley is here and the bottom of the valley is there, yeah? And I don't have to see the mountains that cause this valley. I just need to know the contours of the valley. Agreed? You don't have to have a map including Everest because you're looking at part of France. But Everest is the highest mountain, on that block of land, so you don't need to have the peaks to get a useful map out. And to some extent, this is the peaks. And I'd like to be able to characterize what these guys are like away from the peaks, when you're not on a charge. And it's a bit like I want to be able to find out what's my height there, or what's my height there, or what's my height there. And so I invent the idea of a field. And a field is magnitude. It's a highly abstract thing. It is a measure of the force per unit charge at a point. It's the force that a 1 coulomb charge would feel if it was at that point, but there's no charge there. It's like the contour line. How high am I? What's my field? So it's, in a way, simple. So when you first see it, you think this is no big deal, but then you get tripped up by it because it's not simple. It's very abstract. It is the force per unit charge at a point where there is no charge. You know. So what we say is, if we have a charge, let's get my pen. If we have a charge here, that's the mother charge. That's what's setting up the field. And the field kind of goes in all directions from it. And I imagine putting a charge there. And I say, what force would that charge feel? And then I say, well, the field would be, well, it would be the force felt if the charge was only one charge. So divide by whatever charge I put there. It's got units of newtons per coulomb. But I got to emphasize, you don't need to have the charge there to have a field there. The field is the electrostatic field strength. It's how strong the electric field is at that point. It's like how strong a magnetic field is. So I can write it like this. This is the definition. You divide the force caused by these two charges by whatever charge you used as the test charge. You don't mess with the mother charge, you mess with the little test charge. Or alternatively, you say, oh, it's going to be, well, let's just divide, where's my pen gone? Let's just divide F is equal to Q over R squared divided by Q. It's going to be the electric Coulomb's constant times Q over R squared times R. Very similar to the electric force. And the final thing I'll leave you with is, when you get things that are similar, they are totally confusing. And what you need to do is put them on a piece of paper side by side and compare and contrast them. Force has two charges over R squared. Field has one charge over R squared. Later on we'll do electric energy, electric potential energy and electric potential, and we'll contrast those as well. Let's call it a day there. Remember, we ended at whatever slide that was. 7. We ended before 7?
This is actually slide 12.
No. For the test. We ended, so you know where you're at.